Hello everyone, welcome to our talk. This one is going to be about car hacking today. Today we're presenting our company, PC Automotive, or PCA in short. Our focus is on vulnerability research and penetration testing for various industries, including automotive. Also, we do research and threat intelligence in threat intelligence area and research and development in product security monitoring. And the talk we're going to present today is the joint result of work of many people, pretty much the whole company, plus the special security research team mentioned on the slide. And we, in 2022, to start with, we did a security research for Skoda Superb III, which was the latest generation of Skoda car at that moment in time. Now there is already 4th generation available. And this talk is called Compromise of Modern Volkswagen Group Vehicles, but by modern we mean 2 years old because research takes time, vulnerability disclosure takes time, you will see when we get there. Yeah, and the car was equipped with MIB3 infotainment unit, which is pretty popular among Volkswagen Group cars. It had nice connectivity features you can see on the slide. And as a result of our research, we found like pretty much 21 vulnerability, of which 9 we disclosed already in 2023. And we have advisory about that on our website. And the rest vulnerabilities we're going to talk about today. Those vulnerabilities allowed us to get code execution on the infotainment unit via Bluetooth, then escalate our privileges to root, get persistence, then access the CAN bus of the vehicle, and do some remote control of the infotainment. And by remote control, we mean tracking vehicle location and speed, eavesdropping in-car communication via microphone embedded into the car, then control vehicle sound, control the screen of the infotainment, and exfiltrate some sensitive data such as contact database of the owner. Volkswagen Group does not build infotainment units themselves. They use Tier 1 suppliers for that, and there are several suppliers who provide MIB3 infotainment unit. At least 3 of them we are aware of. This is Precar Connect, LG, and Aptiv. Others may exist. Our talk is focused on MIB3 models provided by Precar Connect, and we didn't verify our findings on models provided by other suppliers. Every automotive component, including infotainment unit, have the part number, which is used, for instance, to replace the broken part in the car. And our research showed the list of part numbers of MIB3 units that we believe are vulnerable to our findings because they are compatible to each other according to information that we obtained from the firmware of the infotainment unit. So they are software compatible. And the further research based on those part numbers shows us the list of vehicles to which those infotainment units can be installed. And the public sales statistics show us that the more than 1.4 million cars of Volkswagen and Skoda were sold in 2022 only, showing us that the impact might be pretty large. So how we did it and our story. First of all, it's good to enumerate the version of the software that we are dealing with. And for the infotainment unit, it's pretty easy to do that. You just can access the system information menu from the screen, and you can see the firmware version of the infotainment. In our case, it was 0304, which we believe was the latest one at the moment we did research in 2022. For other units, it might be harder to obtain software version running because you may know that in car there are multiple electronic units that are actually like embedded systems that have their software installed, the certain version of the software can be updated. So it's not that easy. You have to have some tools. Usually it's done via OBD. You can enumerate versions of those. For infotainment, it's easier. And you can also use and find wiring diagram for the vehicle on the internet. And by those wiring diagrams, you can imagine the architecture of the in-vehicle network. So in the center of the network, there is a gateway that controls several CAN domains, including like powertrain, running gear sensor CAN domain, and others. In the middle of the slide, I showed some components that are connected to this or that CAN domain. If you are not from the automotive world, so CAN bus is very common in the automotive. It's used for connection of the electronic units together and sharing some information, like for communication of them, for talking. So on the bottom of the slide, I showed some controls that would be available to attacker who gain access to this or that CAN domain. For us as attackers, it's important that the infotainment unit has the most wireless interfaces exposed and wired as well. So it's the most interesting block from the perspective of attacker. Let's take a close look at it. And on the left of the slide, you can see how it looks like. The part that controls the screen. It has a part number, it has several connectors for screen, for USB, and it has a main harness, main connector, which has a lot of pins controlling the in-car microphone, speakers, access to CAN bus. Also, it has Ethernet connection to telematic unit and the dashboard or instrument cluster. And it has UART pins. If we take a closer look at hardware numeration, so there is a main system on chip, RCAR M3 by Renesas. There is a wireless baseband. There are two persistent memory storage chips, SPI and eMMC. And on the other side of the board, there is one MCU that controls power distribution of the whole board. So how to obtain software? You can unsolder the persistent memory storage chips, dump them using the programmers I show on the slide. We use those. There are other models available. And by brief software overview, you can imagine the structure of the infotainment unit architecture. So in the middle, we have RCAR M3 SoC, which has multiple CPU cores inside. Most of them are busy running Yocto Linux, but there is one dedicated core which runs FreeRTOS-based CarCom software. CarCom is an internal name, referred in the firmware itself. On the left, we have persistent memory storage, like eMMC and SPI. Then there are some connections to the other electronic units, electronic control blocks in the car. For instance, it's important to know that the RCAR core controls the CAN bus. There are two Ethernet connections, and there are external interfaces. And there's also UART, if you can notice it on the slide. And our first thought was to get access to the UART and see what's exposed. And actually, there is a Linux shell, but it's protected by challenge response authentication based on the RSA. So in order to get access to the Linux shell, you have to know the private key, which was not our case. And well, UART still can be useful for obtaining some system logs. So there is no UART access, no easy way to get shell on Linux system for debugging purposes. So we have to proceed with our research of vulnerability discovery in wireless interfaces.
Okay. Hello everyone. Let's try to explore Bluetooth usage inside MB3 unit. MB3 uses Bluetooth to provide various features like making calls over the mobile phone or playing music. Also, phone book synchronization and message synchronization features can help to make better the communication process for infotainment user, and also Bluetooth is used for some other purposes like Apple CarPlay or something like that. Linux operation system on the MB3 has a service with the name phone, which is in charge of Bluetooth protocol handling. So the protocol handling happens inside user space, and this service is started during the boot by systemd. The following part of the talk will be about this service. So at some moment of the research of MB3, we started to look at the phone book synchronization feature that I mentioned earlier. We to provide ability to exchange with phone books, MB3 unit should contain the code that provides functions of phone book access profile. This Bluetooth profile defines some protocols and procedures that should be when you try to exchange phone books over the devices. So some of the protocols and other stuff you can see on the screen. for example, the devices should have pairing between them to be able to exchange phone books, and also OBIX protocol is used to transfer binary data between devices. Phone book access profile defines the communication process through the client-server model. There are two parts of communication process: phone book service equipment and phone book server equipment and phone book client equipment. Phone book client equipment is a device that tries to download phone books from other device. In our case, it is an infotainment unit. Phone book server equipment is a device that contains phone books. It can be a mobile phone or something else. If we want to send any phone book to the infotainment unit, we need to wait until it connects to us and starts to download phone books because it is client. Luckily for us, infotainment unit starts to download phone books from the phone if they are paired already and the phone did not send phone books earlier. So it's easy to start communicate over this phone book access profile with infotainment unit. Let's look on the content of phone book. Phone book format described in RFC 6350. Phone book is just a sequence of vCard records. Each vCard represents contact of the person. And as an example of this vCard you can see on the screen, and the vCard contains a lot of properties. Some of them you can also see on the screen. So for us, the most important now is a property photo, which can contain the base 64 encoded image of the which represents the photo of the contact. And we found something interesting in the handling of this picture. So let's discuss how the value of this photo property is handled. The contact photo in MIB3 can be seen in contacts menu, and this photo should have a size 100 by 100 pixels. To provide this, it is necessary to scale this photo to these dimensions. It is done in two steps. First step is conversion of original image to the scaled bitmap. And the second step is creation of JPEG image from this scaled bitmap. These two steps are done during initial phone book handling. And on the first step, it is obvious that it's necessary to parse an image. And we found vulnerability in a case when the image has format JPEG. In case of JPEG format, the image parser uses open source library libjpeg with version 9c. So let's look at how the bitmap data is read by image parser. The JPEG parser reads bitmap data row by row. Each row is usually called scanline. For scanline data reading, the function JPEG reads scanlines is used. It's a standard libjpeg API. You can see this on the bottom picture. Before scanline data reading, JPEG parser allocates the memory for scanline data buffer, and this memory has a fixed size 0x4000 bytes. And it is not clear, is this memory long enough to store the data of any image with a really long scanline? So if it's not long enough, so then we can try to overflow the heap buffer and use the stuff to get access to the infotainment unit. So we need to look at this more precisely. So let's estimate the maximum size of the scanline for JPEG format in our case. Each scanline has a size that equals width of the image multiplied by the size of the pixel. And the width of the image for JPEG format, the maximum width of the image is around 65,535 pixels. The pixel size depends on color space that is used in this image. And for a set of non-color spaces for the libjpeg library, the maximum pixel size is 4 bytes. Therefore, the maximum length of the scanline is around 0x3FFFC bytes. And this number is much bigger than the size of pre-allocated buffer. However, as already told, the original photo image has to be scaled to the fixed size 100 by 100 pixels. Because of that, for JPEG case, libJPEG internal scaling feature is used as part of the scaling process. And this feature can make the maximum size of the scanline lower. So it is the usage of this feature is important for us. However, this feature can provide only scaling in 8 times lower. So the maximum size of the scanline will be, in case of usage, this feature is around 0x7FFF bytes, maximum size of the scanline. And this number is still bigger than the size of the heap buffer, and so we have a heap overflow vulnerability in this code. However, we don't know how exactly to control the data inside the data that is written during heap overflow. We can control the length with precision up to the pixel size of this data. However, we don't know exactly how to control the content of this data because JPEG compression can be loosey. Actually, our version of libJPEG does not have any implementation of JPEG lossless compression algorithm. Therefore, we need to deal with loosey compression if we want to write something outside the buffer. The preferable situation for us is when the data before compression, when we're creating the picture, and data after the compression, when the heap overflow is happening. These two data should be the same. However, if we just try to create an image with pillow library, with JPEG color space and some default settings, we did not succeed with this because these two data are completely different in this case. So we need to do little changes in our image creation script. And after several unsuccessful attempts, we changed the color space to cyan, magenta, yellow, black color space, and we set quality parameter to the maximum possible value. This disables some loosey parts of the JPEG algorithm. And this method started working. But only for the images with only one scanline. For exploitation, it was enough, and we use this method to control the data inside the scaling data buffer. Okay, so let's try to trigger this vulnerability on the practice. To do it, we need to create a phone that will send phone book malicious phone book to the MIB3. As fake phone, we use Raspberry Pi 4 to emulate phone book access profile on Raspberry Pi 4. We used an OBX tool from NCC Group, and I want to tell thanks to the guys from NCC Group. It was a very useful tool. Thank you, guys. Okay, so after starting an OBX tool with malicious phone book inside and waiting some time, we noticed that MIB3 unit tried to download phone books and handle it. After downloading, the vulnerability was triggered and crash. We saw a crash inside the logs. You can see this. You can see this crash on the screen. And now we need to find a way how to exploit this vulnerability. So what do we have in this situation? Obviously, we can control the content and length of the data that is written during heap overflow. Moreover, the absence of some mitigations can help us a lot. For example, the main binary of the Bluetooth service is not position-independent executable. Also, control flow integrity and any pointer guard mitigations are not applied to any binary in this to main binary and libgpack library in this case. So from attacker point of view, it's a very good situation, and we try to use the simplest strategy that can be in this case, and let's look at it. The strategy is to try to create arbitrary call primitive and use it to achieve arbitrary code execution. For that purpose, libgpack objects looks very interesting. There are two facts. The first fact is that these libgpack objects are located inside large memory pools on the heap. This is because libgpack has its own memory manager that pre-allocates large memory pools in the heap and uses them to place libgpack objects and manage them. Okay, and after that, and this fact adds predictability to the location of this memory of this libgpack objects, and this helps us a lot because we know the set of pretty large memory chunks on the heap where these objects can be located. And the second fact is that libgpack objects contain a lot of function pointers. It is because we can read in the libgpack documentation that for libgpack it is used object-oriented programming style on C language, and for this style it is necessary to have a lot of function pointers inside the structures. And so because of these two facts, we can use the following exploitation strategy. The first step is to place libgpack object pool after the scanline data buffer. Then we can overflow this buffer with heap overflow vulnerability and override some function pointer inside this libgpack object pool. Then we can try to trigger the usage of this written function pointer and achieve arbitrary code execution by using return intent and jumper intent programming. So we used this strategy, and we was able to get code execution on the infotainment unit. So what do we have now? Phone service has what do we have now? We have code execution on the infotainment unit, but phone service is not privileged service because it has dedicated user identifier and only one additional capability that is not very useful for us. Also, but the service is not sandboxed. Therefore, we have a lot of opportunities how to escalate privileges in this system. After some system research, we decided to choose privileged service as the following target. Before the explanation of next vulnerabilities, I want to briefly describe custom interprocess communication mechanism that is used inside MIB3 infotainment unit. This mechanism is the main APC that is used inside it, and the most services do their stuff through it. This APC mechanism provides the ability to exchange messages between the services on the recurrent M3 system on chip. The basis of this communication mechanism is a service MIB3 root. It has a green color on this scheme. And if any service wants to communicate over this APC mechanism, it should have connection to the service. And to connect to it, Linux parts of the system uses TCP and Unix sockets, and the services from other parts of the system, like from Carcom or some another chips, uses shared memory to communicate with MIB3 root service. So, as example of the usage of this APC mechanism, Linux services can subscribe on CAN events from Carcom chip and receive them and handle in some way. And another example, on the Linux operation system, this mechanism is used to implement remote procedure calls mechanism. So how can we use this information? Luckily for the attacker, the vendor forgot to implement any access control system for this APC mechanism. Therefore, we can send any message to any service, and this message should be delivered successfully. For example, we can try to call some remote procedures through this APC mechanism, and we can call it in some privileged services. So we, at some point of research, we found that there is a shell injection inside networking service, and we call it through this APC mechanism. Therefore, we did it, and this shell injection vulnerability gave us the ability to execute code with networking service privileges. By using these privileges, we can load custom kernel module because Linux kernel compiled without kernel module signature verification. And after using this, we can achieve unrestricted root privileges on the device and execute code inside the kernel. So now I want to show you the demo of the exploitation process. In this demo, we will achieve root privileges on the device. And at the start of the exploitation process, the infotainment is not connected to any hotspot. Then we are starting our exploit. It will send malicious phone book to the infotainment unit. We will achieve code execution on the infotainment unit. And then we will escalate our privileges, and then our payload will connect the infotainment unit to the hotspot, enable SSH for us, and show the image on the screen. So after some time, we will get a root shell on the device, and we can do many other things with it after that. So now we have privileged code execution on the infotainment unit. However, obviously it is hard, so we want to communicate over the CAN bus with it. So our next target is a Carcom chip, which is in charge of CAN bus communication process. Linux operation system processors and Carcom chip has common physical address space, and it can be used in some way. Carcom uses at least two regions of this physical address space. The first region has a gray color on the scheme. This region is used to provide APC over it, and Carcom and Linux use this region both. And they have read-write permissions in this region. The second region that is used by Carcom has a blue color on this scheme, and this region is used to store the firmware of the Carcom, and Carcom executes code from this memory. And the Carcom has read-write execute privileges, obviously, in this region. However, it is not clear. Does Linux have any access to this blue region? And the answer is yes, it has access. Therefore, we can patch Carcom firmware and execute arbitrary code inside Carcom chip. And after that, we did a little work to be able to communicate over the CAN bus. To read from CAN bus, we patched CAN bus interrupt handler. To write to the CAN bus, we simply use the API that is used by Carcom, and the attempts of communication process you can see on the screen. So now we can try to communicate over the CAN with other parts of the car.
Right. Okay, we got access to the infotainment canvas, CAN3, but we actually the next stop on our journey is the gateway. The gateway has the rules to filter the traffic coming from less trusted CAN bus to safety critical CAN buses such as powertrain, running gear sensors, and pretty much does its job very well. So it filters all the traffic that is not supposed to go to other buses. Nevertheless, we achieved persistence. So let's talk about persistence. For persistence, we need to recap like that we have two persistent memory storage chips, eMMC, which has some Linux partitions, including rootfs. But all partitions that have binary files inside that are important, they have Verity enabled and they are readable only. So there is one writable partition /var, but it cannot be used directly for persistence because it doesn't have any binaries on it by default. And there is SPI, which contains some boot executable images, but it's protected by secure boot. So there's choice, either bypass secure boot or Verity. We selected the red pill, and basically we found out that the secure boot is based on ARM trusted firmware, which is a public open source reference implementation. There is on ARM GitHub. There is also fork on Renesas GitHub that supports this ARM trusted firmware for AirCar M3 chips and other SOCs delivered by Renesas. And how it works, how secure boot based on ARM trusted firmware works is that we have two bootloaders, bootloader stage 1 and 2. Bootloader stage 1 is located in ROM, and its purpose is to load BL2 from SPI to RAM to verify its signature based on certificates and to run it if everything is fine. And BL2 basically does the same thing, but for other images such as trust execution environment, CARCOM, and Linux components. To save some space, because we are tight, there is only 32 megabytes. This custom compression mechanism was used. So it's not part of open source reference implementation, but the developers of the system decided to use compression. And let's take a look how this compression image format looks like. So there are a couple fields. Most important for us is that in the compressed image, we have the size of the compressed image and size of the decompressed image. And on the bottom of the slide, you can see the format of the certificate, at least partially. So there is just one important field for us here is that there is image size also in the certificate. And how it works, that decompression is happening before the signature verification. And as a result of decompression, we get rid of the compressed image header. We use the size and the loading address from the compressed image header to load and decompress the image. But for signature verification, we use size from the certificate. And if we write to SPI memory any arbitrary compressed image, change the header to become larger. So the first part of the image will be the same, but we append a malicious part to the end. The signature verification will still pass successfully, but the content will change, right? And how can we use that? For instance, we can append some data to the init.rd image, and once it's being decompressed, it will overwrite already running CARCOM image, which was already loaded, verified, and it's running. So we can hot patch the CARCOM, for instance.
When we were trying to modify the CARCOM code, by using this vulnerability, we noticed that Linux kernel generates an error that is related to the init.rd image. And this error tells us that init.rd is not in a good state. And obviously it is because we appended the additional data to init.rd. And Linux kernel interpreted this init.rd data as part of it. So how can we use this fact? Let's look at how init.rd is used inside MIB3. Linux kernel uses init.rd to store temporary rootfs content, and Linux kernel extracts init.rd during the boot process to the RAMFS and calls init script from init.rd to mount the main root file system with the Verity with integrity check enabled. Okay, let's try to use this fact. We need to look what can we do. Let's talk a little about initrd format. This format is CPU archive, which is just a sequence of file records. Each file record contains file metadata and the data of the file, and file metadata contains path to the file, size of the file, and etc. CPU archive should have also CPU archive should have last record with name trailer, and if common CPIO unpacker reach the record with this name, it should finish the unpacking process. However, Linux unpacker of the initrd is not finishing the unpacking process in this case because it wants to handle all the initrd data. Therefore, we can append the additional CPU archive to the original initrd image by using the last vulnerability, and this CPU archive will be uncompressed to the temporary root FS during boot process. Moreover, Linux does not check the existence of the file with the same file name during this unpacking, and because of that, we can try to overwrite original init script with our script, which we will place inside additional CPU archive, and the Linux should overwrite the original script, and after that, Linux will try to use init script to mount real root file system, but it will execute our commands after that. So we achieved persistence because now we can execute code after the reboot of the system. And you can see the results of the code execution after the reboot on the screen. We can disable authentication on the OAuth interface for login application. Also, we can run our agent after the reboot and do some payload.
Yeah. All right. So one important note to take is that how to modify the SPI content. Well, since you have unrestricted root on the Linux file system, on the Linux system, you can just patch the SPI image through the driver. So it's possible as part of the attack chain demonstrated. And finally, let's talk about phone database. As we know, the infotainment unit stores phone database. And it's stored in an unencrypted format. So it's once you have code execution infotainment unit, you can actually get access to that, right? And let's take a look at full attack chain. So we need one-time access through Bluetooth. We need pairing, it's required, to get code execution, get persistence, get access to CAN bus with restriction that the gateway is filtering traffic further, so there's no safety impact. And last important piece of puzzle is how to exfiltrate the data to the internet, right? So for that, we can use the automotive Ethernet connection with the telematic unit, which is actually a modem which has eSIM, and it's connected to the cellular network. And not all traffic passes, but for DNS traffic, there were no restrictions, and we were able to exfiltrate data by using DNS command and control. And I would like to show you the video demonstration on the real car. So for the purpose of demonstration, we developed a system with the UI that can control the car. Okay, Bolosh, we're all set. Once it's already infected,
I'm starting monitoring now. Tracking started. We see you moving.
Do you see the speed?
Yes, 9 km/h. It's now 8.
Let's do screenshot.
Alright. I'm starting screenshot now. Okay, we receive screenshot.
Screenshot received.
Yes.
Okay, perfect.
I am starting the phase now.
Okay.
We good.
I am stopping the phase. Now.
Received.
Hit stop.
Alright.
Okay, Walsh, we are ready to test audio recording.
Starting audio recording.
This is PC Automotive and we are testing audio recording in Skoda.
Alright, audio recording stop. Okay, I start downloading now.
Testing audio recording in Skoda.
I play audio in the car.
This is PC Automotive and we are testing audio recording in Skoda.
I am proceeding to contact database.
Just a second. Yeah, I opened it on my end. Please go ahead.
Contact database received.
All right, we are done.
All right. We don't have time for all the rest, but here's the list of identified vulnerabilities. You can see it closer later when you get access to the PDF of the slides. And we have some attack chains prepared. We didn't cover all the vulnerabilities today because of lack of time, but they all lead to this impact that was demonstrated, what is important. Also, we have some disclosure timeline with Volkswagen. Finally, I would like to say thank you for contribution to all the team and to Volkswagen Cybersecurity Incident Response team for handling our findings and making this talk possible. Thank you. We have the, yeah. We have this system live that you shown on the video, but not with the full car, with just infotainment unit. Feel free to find us later in the hall if you want to show the hands-on demo, let's say. Thank you.